we're taking a second look at stereo nets and more things that you can do with them. So we're going to look at what you can do to have more bedding planes on the same stereo net without it getting so crowded that it looks like Spider-Man drew it. And we're also going to look at what you can do if you don't have nice perpendicular angles to look at everything, because in nature, not that much is perpendicular. So, okay, the screen is working now. So last week, you guys learned that you can show a bedding plane as a curve on a stereo net. So you're taking something in 3D space and turning it into a 2D picture that's just, it's a curve in your circle, and it tells you exactly what the orientation of the plane is and what the dip angle is. Unfortunately, if you get much more on there than what you did last week, where you had like 4 curves on the same thing, it starts getting confusing. And some of you were like, oh, am I looking at this one or am I looking at that one? Because the curves were close to each other. And when you went to label them, it was easy to make a mistake. So it can get really crowded. So wouldn't it be nice if there was a simpler way that didn't make your stereo net so crowded?
Yeah.
Yeah, of course there would.
I've been looking for years.
Well, if you think back to calculus class, yeah, everybody can groan. A plane can be represented uniquely by a line perpendicular to the plane called a pole. If it goes through the origin and is perpendicular to that plane, there's only one line. Therefore, that line is unique to the plane. The plane is unique to the line. We can plot these poles on a stereo net and skip drawing the curve for the plane, because since it's a one-to-one, only one line for that plane, if you draw the line on there, you don't need to draw the plane. But because we're looking for a line, we're not having a bearing and plunge, this thing is perpendicular to your plane, we don't even have to have as much as we were for like a bearing and plunge line. All we need is a point, a single dot on your stereo net, and it's equivalent to that big curve you had. You can fit a lot of dots on a stereo net pretty easily without it getting cluttered. So since it's perpendicular to the plane, all you have to do is when you have it set up so that your curve would be going from the north to south pole as you draw it, when you count in, say your dip was 30 degrees, you count in from the edge 30 degrees, count an additional 90 degrees straight across the equatorial line, and put your dot. So yeah, you'll always go past center, always. If you didn't go past center, recount. This point, no connecting lines or anything else, just that point, is equivalent to one of those great circles that you plotted last week. So for example, this one here shows a strike of north 35 degrees east and a dip of 25 degrees southeast. We can put a little dot right where that little plus mark is here in the center that's labeled pole. That dot represents the exact same thing. It might be a little tougher to read, where last week, at the end of the lab, you looked at some circles that just had a great circle curve drawn on it, and you could figure out the strike and dip just by looking at it. With the dot, it takes a little more practice, but all you have to do is turn it so that it's on the equator, and then you can backtrack and visualize the curve and get your strike and dip. The other cool thing we can do with that is we can find planes that are perpendicular to it. So, if I have this table surface here, this plane is perpendicular to it, and this plane is perpendicular to it, and this plane, and so forth. Lots and lots of perpendicular planes. One thing they all have in common as long as they're going through the origin, is that they contain that pole. No matter which way I turn this, as long as it's perpendicular, it's containing that pole. So if we have a great circle, this one going from north to south right here, and its pole is over here on the left, any other great circle curve that goes through that point, i.e. contains it, is perpendicular to your first plane. This is not always necessarily obvious why we care about planes that are perpendicular to each other, but for engineering purposes especially, a lot of times you want to know perpendicular. You want to go through that thin bed perpendicular instead of at an angle, or you want to make sure something else meets up and is perpendicular and so forth, or the road cut, or whatever the case may be. The mine shaft. You don't want to hit at an oblique angle and have a blowout, or whatever the case may be. Being able to figure out perpendicular lines this easily for all the planes, no equations, no calculus or anything like that, can be really useful. The other thing, more useful on average maybe to a regular geologist rather than a geological engineer, is figuring out when you have a parent dip and want the real dip. If you have a sandstone bed and you can see part of it in an outcrop, unless that outcrop is perfectly perpendicular and cutting it like the edge of a book, what you see exposed in that outcrop isn't the real dip of that bed. Any other angle other than perpendicular to it, perpendicular to the strike specifically, I should say, is going to show a different dip. So like in this block diagram, on this side, right where the letter T is, you can see the real dip of the bed. It looks like 45 degrees. If we have a road cut where wall 1 is, it looks like the bed is dipping at 33 degrees. And if we have it where wall 2 is, it looks like it's dipping 19 degrees. If that's the only exposure you have, and you make an assumption that, hey, this plane is dipping at 19 degrees, so half a mile away I need to go this deep to drill my well safely without puncturing that layer, you're either going to drill too far or not far enough. You could go deeper if you needed to safely. It's important to know what the real dip is. So if we have the strike, there is some surface exposure, and we have just one apparent dip, we can find out the real strike and dip using a stereo net. You don't need to know what angle that wall was. That would if you were going to do it with geometry, you'd have to know exactly what angle that wall was, and then do some fun calc and trig and geometry type stuff to calculate what the strike and dip was. This you can just do it, not worry about the angle. All you need is a strike and what the angle apparently is on that exposed wall. So you mark your strike line just like normal, and then draw a tick mark on the other side, so you have both ends of your strike line, like we did last week. And then using the apparent dip, treating it, you've got a bearing and plunge for that. Like if we're looking at wall 2, we would say, the bearing looks like it's about north 60 degrees east. That's the bearing of that wall. And the apparent dip is 19, so that's our plunge. We can get the mark for our bearing and plunge and put a point there. Don't connect it like we did before, because we don't care about the actual bearing and plunge. It's just our apparent dip to get where we want. Turn the paper so that the strike line is on the north-south pole, kind of like you did last week. Except this time, instead of counting in a certain number of degrees to draw your great circle, just find the one that your point is sitting on. That's your great circle. Once you draw it, you can read your dip, because wherever that circle is, you just count in from the edge. Got a picture of it. So here's our strike line. You know, this one, I think I did north 15 degrees east. While it was there, I did a bearing and plunge. You know, I had to turn it, but the plunge, or the bearing was 160 degrees in azimuthal. And I don't remember what the plunge was, but I had it lined up, had the plunge. And then I turn it so that my strike is in the north-south orientation. I find the curve that you would see if this was good tracing paper instead of bad stuff, but there's a stereo nut under it. Trace my great circle that intersects that point, flip it back to normal, I'm all set. Okay, it was 20 degrees. While you're here, you can find out the dip just by counting in from here, you know, 10, 20, 30, 40, 50, 60, maybe 65 degrees or so it looks like without having the actual stereo net behind it. So now we have a strike of north 20 degrees east, dip of 65 degrees, starting with a strike and an apparent dip on some road cut. Sometimes you don't even have a strike. You don't know where it intersects the surface, or there's grass and trees and parking lots and stuff in the way. But you've got two different road cuts. You know, there's a road cut on the left and a road cut on the right, or left and right, of the highway. And they're at slightly different angles. That's good. Now you have two different intersecting walls. You have two apparent dips. That'll work. So you do kind of like you did in the first one, where you take the bearing and plunge on the one apparent dip and put a dot, then go ahead and do the bearing and plunge for the other one and put a dot. No lines at all so far, no strike or anything like that. But you've got two dots. There's only one way that you can spin your paper and have the two dots fall on the same great curve. Well, I guess technically two ways, one on the east side and one on the west side. But it'll be the same curve. So you rotate your paper until they show up on the same circle, the same great circle, and trace that one from the North Pole to the South Pole. Now you have a strike and dip line that you can read. So to step you through an example, the apparent dip on wall 1 has a bearing and plunge of 16 degrees and north 40 degrees east. Second wall, we have 30 degrees and north 100 degrees east. So if we follow those steps, using the two apparent dips, we'll find the strike and dip of the bed. So I mark the two bearings. One at a time, I turn them and count in for the plunge. And there's the second plunge, those two little red dots on there. Then I rotate it until they line up on a great curve, and I trace it. While I still have it in this orientation, I can now count in from the edge to see how many degrees that is. I can rotate it back so that north is at the North Pole. Count down 10, 20, 30, 40, 44 degrees, and I have a strike. So strike and dip is north 44 west, 30 degrees northeast. Just from those two road cuts, no geometry or trig or anything like that. So that's actually very useful when you're doing field work. That's probably one of the things that they'll have you do in field camp when you're trying to do field mapping, depending who your instructor is while you're there. So in today's lab, you've got some strike and dips that you'll have to plot the poles, find perpendicular planes to the original plane that I give you, plot the poles to those planes. You've got some strike with one apparent dip. You've got some that are two apparent dips, and you'll then find the strike and dip of those. So that's what you've got. Parts 1 and 2 are on the first piece of paper, and then part 3 is on the second piece of paper. And every step has a different letter like capital or lowercase, so you can use those to label, so you don't have to have it all cluttered up with writing strike and dip and stuff like that. Just use the letter labels on there. So with that, we should be able to get started.